EAnoise actually was EAnoise initially, but as I was developing and studying more deeply on the subject, I increased the key on the method. Is an in-situ surface impedance measurement. And I don't have much time, so I use low-cost instrumentation. And what is surface impedance? We'll be talking about this all morning or afternoon. I don't know where you're at. But by definition, the surface impedance is the pressure divided by the particle velocity at the interface between two means. And I don't know about you guys, but I don't measure in water. Unfortunately, I would like to measure in water. And these two means is actually normally a sample size material with the air. So this interface right here is where you can put this relationship, pressure and particle velocity. And why measure the surface impedance? So
Sidney, sorry to interrupt, but if you could put your presentation in full screen, it would be, if it is possible.
Oh, sorry.
Of course. Yes, sorry for interrupting.
So why measure the surface impedance? With this quantity is acoustic quantity. So for acousticians is important because we can calculate the reflection coefficients and the absorption coefficients. When you can use all this data to numerical simulations, like the work that's been doing by Finner, Luis, and also Renaud. I think Jochen Vey also use some numerical simulations, and we can see the phase shift characteristics of the material. We can use the absorption information to estimate the reverberation time using Sabine's formula. And particularly for me, I find very useful to measure this information, the surface impedance, to estimate material characteristics. That is valid mainly for porous materials. There is a fine work done by Dr. Paulo Maresi, our professor and co-advisor of Luis, that he could, with the measurements made on impedance tube, estimate the 5 parameters of the porous material. So I also been doing relative work on this. And for me, as a manufacturer, as a small manufacturer, I built my own acoustic treatment devices. I identify the product performance in prototype stage. So what that means, I can, with this technique, at least I presented for you guys, I can build a small sample and measure a small prototype, measure and qualify what I predict in terms of absorption coefficient or surface impedance. And it's okay, now I produce more of that material. And there is a lot of measure techniques that I've been studying on the past 3 years. There's an outlier here. I think that you all know that ISO 354. It's not on this group because it don't retrieve the surface impedance, but is a characterization method of acoustical properties. We can retrieve the absorption coefficients and in the reverberant field. And that's the main differentiation of this method. And it's very simple, but it's very costly because you need a high sample size for this, for the prototyping stage. That will be unfeasible because imagine that you have to build 10 to 14 meters square material, test it, don't work. So you have to build another 10 to 12 meters square. So not feasible. And you have the impedance tube method defined by the norm 10534. If I'm not wrong, correct me if I'm wrong. It can be more costly if you're going like he now presented here, measure on the lower frequencies, but it can be less costly if you use lower precision instrumentation. And that's why I put this group right here, the PP system. Why PP? Because it uses 2 pressure microphones. And because I have only lower precision instrumentation, I put on this lower cost relationship. But it could use a little higher precision instrumentation and be a little more costly. And you have the PU system that will be more costly and more complex. I talk for me because I tried to measure the absorption with this system and I could not retrieve I could not make this work. And is a very costly and complex way because use a unique sensor that retrieves the pressure and the particle velocity on the same point. And that was developed, I think there is only one sensor that on the commercial, on the market. And you have this frontier of complexity, that's the array system measurement techniques. That is where Eric Brandão is right now. Dr. Eric Brandão is also my advisor. And imagine that, imagine the complexity. A robot acquiring 128 points of pressure, and that will generate a data that you have to, a non-quadratic matrix that you have to invert. And that's a very complex task to do. So I'm right here. That's what I focus my study. The EAnoise, the initial technique that I studied. That the most simple and practical way I will explain why is that the most practical and least complex and least costly way to measure surface impedance. There's the PWA and K-term, and there is the EAnoise that will be my contribution to this topic. Basically, I will talk about this. The EAnoise was developed in 2002, and 2005, for this about 15 years ago. And why is so practical? Because you don't use a sound source. It considers the ambient sound of the reverberant fields. And when you don't have the sound source, it becomes a more practical way of measure. And you need only 3 parameters: the relative position between the microphones, so this L spacing L, and the distance of this microphone to the sample, and the transfer function or the spectral division between them. This enters on this equation that deduces from the plane wave assumption, considering that you averaging the angles of incidence because you don't know where the sound is coming from. You don't know the angle of incidence. The main thing that was achieved here was to remove the angular dependency of this equation. And that's worked very fine because we record these 2 points of pressure for 30 seconds and calculate a transfer function for each second that will average not only in time the pressure, but the angular incidence. 1 second you have one incidence, or second you have the other incidence. When you take 30, 60, no, you can measure for a longer time, but you don't need. You average, you smooth the data. And what will be causing this, that will remove the diffraction effects that is common on in-situ measurements. And on this technique, you have to invert the microphones and measure again, because the microphones are inherent different and you cause phase differences that will provide uncertainties on the measure. When you invert it, you remove these differences and you calculate the geometric mean of these transfer functions to input this transfer function on this equation. The key term method developed by Brandão is a more complex method and assumes the spherical propagation, the model that was developed by Dean Gilbert. This little equation here, it represents this geometry right here. You have a source, the incident wave pressure is this term, the reflected wave is the pressure is generated by this term, and this last term is the dissipation energy caused by the sample, assuming locally reactive samples. So on this method, we also assuming the local reactive samples, because don't matter the incidence of the angle, the wave, we all enters the sample size with the normal incidence. So right here is where we can see the surface impedance. He uses this function to on this one algorithm, an iterative algorithm that creates a new field, but generates by one monopole. With these new fields, he takes a new measurement, a new transfer function. He compares the transfer function measure with this new simulated transfer function. If they are similar, then the impedance, the surface impedance initially put on the here will be the measurement surface impedance. This initial estimative can be calculated using some plane wave assumption that he uses the PWA. What I use is the EAnoise. So if there's not similar, a new estimated is calculated using the second method. And what I've done was to sum these two works, the key term with the EAnoise. And basically I built this dome. Consider this spherical dome, and this region right here is the sample. It's a product here, is a aluminum's product. I don't know where I get this image, but I think that can represent the dome very well. And what I did was to put a sound source in each point of this, creating this spherical dome with a lot of sound sources. And not also that, I multiply this random pressure for each one of these sound sources. So what I've done in with an analytic equation was to build a reverberant field. This equation right here describe the pressure at one point for this reverberant field simulated in a simulated way. And some results. I use, so only for what I've done was to adapt this equation for the reverberant field, for the diffusive field. So on this algorithm, what I adapt was this step. And this estimate, I use EAnoise, and this step, I use this equation. So for my results made on reverberant fields, I have this early stage results that's in Portuguese. I'm sorry about that. But the black line is my reference. And as you can see, the gray dotted line, the lighter gray dotted line is the EAnoise. So the darker dotted gray line is the k-noise, the robust method algorithm, iterative algorithm method. And as you can see, for the lower frequency, the surface impedance can get a little more closer to the reference for the imaginary part and the real part also. But what about the absorption coefficient? As I'm a consultant acoustician, I actually provide more feasible data for my clients with the absorption coefficient. So I built this Helmholtz resonator, slotted Helmholtz resonator, a big one, and predicted the absorption coefficients using the transfer matrix method model that was presented by Rinald right now, and measured only with the EAnoise, the first technique. And as you can see, I could validate what I project for my clients, at least for the two first peaks that was I aiming for. I was aiming for treatment and 100 to 200 hertz. And that's that. The higher frequency discrepancy that have is because the EAnoise method works only to up to 2 kHz. And the model is plane wave assumption and have some limitation also when you compare to experimental data. What I could achieve with the EAnoise was to improve the measurement of the absorption coefficients up to 5K. And this is a result comparing with the, it's the same material, the three lines is representing the absorption coefficient of the same material, but the green line represents the measurement made using the ISO 354, using 10 to 12 meters square of material. The EAnoise was the initial technique that I studied. And as you can see, after 2K, he starts to decay the absorption coefficients, what is not actually what's happening for the absorption characteristics. But for the lower frequencies, he characterized well. And with the EAnoise, I could improve the absorption coefficients, make the method more robust to retrieve the information above the 2 kHz. And you can measure it with songs because we assuming the reverberant fields. The EA represents environmental anonymous noise. So it's an unknown signal on a reverberant field. So what I've done was to put some songs and measure the material. It's not very effective. Depends a lot on the energy spectrum of the song. But as you can see, for 300 to 2K, it's worked just well. And that's maybe only what you need. And if you want to improve the measurement with songs, put sweeps on. And that's that. There are some limitations because the model that I use for this iterative algorithm needs the source location, and the initial consideration of the EAnoise, you don't know where the source is, but this can be controlled using sound sources to excite the reverberant field. So you also have the sample size. because the model considers that is an infinite sample. The absorber, the porous materials is infinite on the model, what is not real at all. And you have this limitation of the PP system, that is the pressure difference. For lower frequency measurements, it's difficult to achieve, it's difficult to measure because you have very high wavelengths and you have very low spacing. So when, for instance, 17 meters high wavelength passes in 2 microphones space in 1 centimeter, what is going to be measured is basically the same pressure. So that will carries a lot of uncertainty for the lower frequencies. That is why it's so difficult to measure the lower frequencies. And some measurement tips, what I could achieve to improve my measurements was to excite the sound fields with at least 2 sources emitting sweeps. The sweeps was the best. I put a sweep looping in 6 seconds, so measure about 5 sweeps. Moving sources can remove the modal effects because you have different locations in a room, so that will generate different FRFs, like the Luis was talking about. Have different source location, different FRFs, different pressures. When you moving, you analytic physically is moving the data. That is very nice to see. Position or moving the sources far from the sample. And for lower frequency measurements, I found the filter pink noise on the spectrum that you want to measure is better than sweeps. And you need to use a higher microphone spacing because the issue that I addressed just on the previous slides. And that was that. Any questions? I hope that I was in time. I think
yes.
I'll talk a little faster.